So thank you all for being here today. Sort of briefly scan the list of attendees, a few familiar faces. So thanks for taking time out of your day to be here. As Brandon mentioned, brief discussion presentation on low carbon concrete. As Brandon mentioned, I'm Senior Concrete Materials Engineer at Harbourside Engineering Group. The division of Harbourside that I work in is called W.S. Langley Concrete Materials Technology. W.S. Langley, Dr. Langley was an independent consultant for over 30 years. He's been in concrete industry for 60 plus years. Was an independent consultant up until about 2 years ago, in which Harbourside acquired W.S. Langley, at which point I came on board. For the time being, we're keeping the name W.S. Langley Concrete Materials and Technology, a division of Harbourside, just because a lot of our clients throughout the U.S., Canada, and Europe know the name W.S. Langley. So for the time being, there's no reason to change it. So if you see W.S. Langley Concrete Materials as of just under 2 years ago, they're a division of Harbourside. So let's talk about concrete. Believe it or not, if I were to say concrete is a low carbon material, you perhaps might not believe me. If we look at this figure here, embodied carbon, sort of by a unit mass basis compared to other materials, concrete is actually a low carbon material. So we have embodied CO2 on the y-axis, embodied energy on the x-axis. This banana shaped figure in the bottom left. Let me see if I can use a cursor here. Bottom left is concrete, and sort of compared to other common building materials, you can see that their embodied energy and CO2 is higher. Concrete, however, is the most widely used building material in the world, second most consumed material to water. So obviously we need a lot of cement to produce concrete. And if you're on this call and you don't know what the difference between cement and concrete is, cement is to concrete as flour is to cookies. So cement is the raw ingredient that we need to produce concrete. And because of the large amount of concrete we produce on an annual basis, this figure this number slightly changes year over year, but it's a fairly off-quoted stat that the cement industry is responsible for 5 to 8% of CO2 emissions worldwide. This number is slightly smaller in Canada, around 1.5 to 2% in Canada. And if we look at the volume of cement that is produced on an annual basis, up until last year, approximately 4.7, just under 5 billion tons of cement were produced. Now, the production of 1 ton of cement essentially releases about a ton of CO2 in the atmosphere. So because of the large amount of volume of concrete used on an annual basis, the amount of cement produced on an annual basis, a lot of work around Canada, worldwide, is looking at ways in which we can cut emissions. And I recommend you, if you're interested in sort of learning more about what the Cement Association of Canada is doing, what other agencies are doing around the world, Cement Association of Canada has a publication here on their website that's available free to download. And essentially they look at the 5 C's. So reducing clinker, cement, concrete construction, and carbon uptake, many of which we'll sort of touch upon in today's presentation. So perhaps the biggest buzz in the concrete industry today is low carbon concrete. If you attend any technical conference on concrete, if you scroll on LinkedIn, if you search concrete on Google, you'll likely sort of come up with low carbon concrete. And certainly there's sort of a big push lately to specify low carbon concrete on jobs, to use it, but many people don't know really what it is. And hopefully throughout this presentation, you'll have a better idea of what low carbon concrete is, how we develop or how we mix or what ingredients we use, how we specify it, how we benchmark it, and then we'll finish off with a little case study from here in Atlantic Canada. So Concrete Ontario, perhaps you could argue, is sort of one of the leaders of implementing or defining low carbon concrete. And Concrete Ontario, as of last year, defined low carbon concrete as concrete produced with a reduced carbon footprint, compared to typical mix designs while still meeting all necessary performance standards. So schematically, what does this mean? Here I have 2 cubic meters of concrete. So 1 cube on the left, obviously 1 on the right. So back to our definition, we're not compromising performance at all. So performance, you can think of strength and perhaps a durability requirement. So on the left, we have what we'll call traditional concrete, ordinary Portland cement, fly ash, water, admixtures, obviously aggregates. This mix achieves a compressive strength of 35 MPa, which is required per CSA to meet C1 requirements. Also has a permeability of 1,500 coulombs. It's essentially a prescriptive requirement that's within CSA 823.1, which we can call our concrete specification Bible in Canada. Essentially, this is a typical concrete used on a bridge, for example. Without compromising durability, we can achieve a low carbon mix by really using the same materials, but proportioning them in a way to have a lower global warming potential compared to a traditional mix. And you may be wondering what a GWP is. We'll certainly learn all about that throughout the presentation today. So essentially, we're not compromising strength, 35, 35. We're not sacrificing our exposure class C1. We're not sacrificing permeability, 1,500. We're essentially optimizing a mix. We're developing a mix, perhaps not using novel materials, not using really anything, any special materials. I mean, certainly those are available, but you can see these materials that we're using are really no different than these materials here. We'll talk about what Portland cement is, what GUL is. However, we're achieving a global warming potential of less than 15. Essentially, we're developing a mix that has a lower emissions than this cubic meter of concrete. So when it comes to strategies for low carbon concrete, I mean, certainly there's a number of methods. Certainly we don't have time to go through all of these in detail today, but want to sort of stress on a few of them. An easy one is adjusting the age strength of a mix. So if you're a contractor, or if you're in the audience and you've read a concrete specification, you'll likely see a line item in the concrete spec that states concrete on a job must exposure class C1 for a bridge column must achieve 35 MPa in 28 days. I mean, it's fairly traditional for concrete specs to specify a strength requirement at 28 days. However, let's say the structural element doesn't need to be loaded until 56 or 91 days, or put into service for 56 or 91 days, then we can optimize the mix. We'll still achieve strength of, let's say, 35 MPa, but if we can achieve it at a later age, we can essentially make the mix greener. We can add higher levels of supplementary cementing materials, which we'll talk about here in a bit, but we can still develop a mix that will still achieve strength, but at a later age. And in doing so, we can essentially create a lower carbon mix. The next is performance-based specifications. So back to specifications, likely you've read a specification or two. There's prescriptive and performance-based specs. So prescriptive specifications, the concrete section of a spec might read, the concrete must have a minimum cement content of 400 kilograms per cubic meter, must have a maximum fly ash content of 20%, must have a maximum water cementing ratio of 0.37. These are very, very prescriptive requirements. If instead we have that in specifications and we have performance-based specifications, essentially all they state is the end goal requirement. And in doing so, it gives freedom to ready mix suppliers who are brilliant at optimizing mixes to develop a mix that still achieves the same performance requirements. So they'll still achieve the 35 MPa, they'll still achieve your 1,500 coulombs at 91 days, or whatever the exposure class permeability requirement is. However, they have the freedom to perhaps use a lower cement content or a higher replacement of fly ash. They're not nailed down to the very prescriptive requirements. And the issue with sort of specifications, and if you're on this call, sort of, I've said a million times if you've read a specification, but specifications are often copy and pasted from 10 years ago. So 10 years ago, no one had a concern with this specification. So copy and paste, let's put this section in this new specification. Unfortunately, in doing so, with now sort of the push for low carbon concrete, unfortunately, there's sort of a lot of these, and I read specs on a daily basis. And I mean, often we still see a lot of prescriptive base specs. Material efficiency relates to member size. If we can develop sort of a suspended slab that's perhaps a little thinner, or the column diameter, if we can reduce that, essentially will decrease the volume of concrete. And then one thing that I'll sort of focus a bit on the next few slides is mixed design considerations. So the industry lately has moved away from ordinary Portland cement to Portland limestone cement, which we'll talk about here. A lot of concrete mixtures for various applications include supplementary cementing materials, which we'll talk about, alternative supplementary cementing materials, or in the precast industry, most precasters, if not many, use what are called blended cements. Aggregate optimization, if we can optimize the aggregate gradation, maybe bring in a third aggregate. If we can increase the aggregate volume, we decrease the paste content, we decrease the paste content, we decrease the powder content, we decrease the powder content. We not only decrease the cost of the mix, but we make it lower carbon. Use of admixtures. Admixtures are widely used. I mean, it's hard to find a given concrete mix without some type of admixture. Obviously, air enchainment admixtures essentially allow us to air enchain our mixes. Water-reducing admixtures, essentially, as the name applies, allow us to maintain our slump but decrease our water. If we decrease our water, we decrease our water cementing ratio. Decrease our water cementing ratio, we decrease our cement content. Lower cement content, lower carbon mix. And then finally, recycled concrete aggregate. So recycled concrete aggregate, there's a section now within CSA A23.1. Mainly sort of a lot of where I see RCA used is sort of bases of road bases, but I mean, there are a few applications where it's being used more and more in structural concrete. So if we elaborate a little more on mix design, a given concrete mix is essentially comprised of the following four constituents. Obviously, we need cement and water to essentially hydrate together to form the glue that holds the aggregate together. And admixtures, as I said, if we have concrete exposed to freeze thaw, we need air in it. There's a lot of novel, incredible admixtures out there, whether it be shrinkage reducing, superplasticizers, water reducing, viscosity modifying admixtures, really depending on your application, if you're placing concrete underwater or architecturally or SEC, or I mean, there's a plethora of admixtures available to essentially give you whatever elastic properties or plastic properties you want in your mix. Now, by volume, cement is fairly small compared to aggregate. I mean, obviously your admixture volume is very small, but even though cement only accounts to 10 to 15% by volume of a given mix, it accounts for approximately 85% of concrete emissions for a cubic meter of concrete. So if we can find ways to optimize the cement component, then we can essentially significantly drop the emissions in a cubic meter of concrete. And there's certainly a number of, I'll call them powders, that we can use as an alternative to ordinary Portland cement. So ordinary Portland cement certainly has been around for a long time. Within the past, we'll call it decade, Portland limestone cement was introduced, and we'll be talking about here what Portland limestone cement is here in a second. In addition to Portland limestone cement, Most ready-mix suppliers use one or more supplementary cementing materials. SEMs are essentially bought naturally or processed pozzolans that either react hydraulically with water or pozzolanically with calcium hydroxide to essentially increase strength and improve durability of a mix. I mentioned some of them are byproducts. Fly ash is a byproduct of coal combustion. So New Brunswick Power up in Belledune, New Brunswick, they process coal. A byproduct is fly ash, and they sell and they produce a very high quality Class F low calcium fly ash that's used by a lot of ready mix suppliers here in Atlantic Canada. In Western Canada, since they also burn coal, they have fly ash available. In Central Canada, like Ontario, they don't burn coal, so they have something known as slag. So slag is a byproduct of metal production, essentially. So a lot of ready mix suppliers in Ontario, for example, they'll use Portland limestone cement and slag, whereas majority of ready mix suppliers here in the land of Canada use Portland limestone cement and fly ash. Now, in applications like marine environments, like the Confederation Bridge, for example, you require, or many use, what's known as silica fume. So silica fume is a byproduct of silicon metal production. It's approximately 100 times finer than Portland cement. So it's very effective in giving high early strength, but very low permeability as well. So the mix design used for the Confederation Bridge was Portland cement, fly ash, and silica fume. Now, recently, CSA adopted glass pozzolan. So we'll be talking about glass pozzolan here in a second, but we'll learn there's essentially three types of glass. Beer bottle glass, for example, being one of them. If you crush it down fine enough, you can use it to react pozzolanically within concrete. And then the last one is natural pozzolans. So as the name implies, they're obviously natural, volcanic ash, metakaolin, pumice. Currently, there's no source or manufacturer in Atlantic Canada. However, certainly in areas like Saskatchewan, for example, I mean, there is a source, and perhaps as there's a big sort of question now regarding what's going to happen when coal combustion shuts down. I mean, many have said 2030 or 2050. So when coal combustion does perhaps stop, what's going to happen to fly ash being available? Next is blended cement. So many precast suppliers, instead of sort of blending silica fume and fly ash into a cement, you can purchase what's known as blended cement. So essentially, it's a blend of Portland cement, slag, and silica fume, or Portland cement and slag, or Portland cement and slag and silica fume. Essentially, it's sort of a binary or ternary mixture mixed together. So many precast suppliers, it's certainly easier for them to just use that to achieve sort of high early strength for stripping, but also a very high strength, but also low permeability for C1 and CXL exposure classes. And then the last three are sort of specialty cements: calcium aluminate cement, calcium sulfide aluminate cement. I have a PhD thesis on those two if you need something to put you to sleep tonight. And then magnesium sulfate cement. These are sort of cements used for sort of niche applications, but they're essentially produced by burning them at lower temperatures. So they essentially reduce lower emissions compared to sort of ordinary Portland cement. So what is Portland limestone cement, you may be wondering? So if we look at the top figure, the rectangle on the top, that's essentially the breakdown or composition of ordinary Portland cement. So back to one of the figures at the start of the presentation, the rotary kiln that I showed, that's a rotary kiln at Brookfield here in Nova Scotia. So that kiln, or that cement plant, is essentially located adjacent to a limestone quarry. You essentially extract limestone. There they have a high and low grade that's essentially needed that sort of makes up the lime, iron, silicon, alumina needed to produce clinker. So you essentially take those ingredients, you feed them into a rotary kiln that's heated to 1450 degrees Celsius. What comes out is clinker, which is essentially the size of a golf ball. You crush that up, you blend it with gypsum. Gypsum is needed to avoid your clinker from flash setting. So if you didn't have gypsum in there and you added water to it, your powder would flash set. Then in 1983, CSA sort of had a green push back then and adopted up to 5% limestone. Now, Portland limestone cement sort of adopted within the Canadian industry, sort of within the past decade or so. I believe all but one cement producer in all of Canada, all of them produce Portland limestone cement. I believe Cement Quebec is the only cement producer in the country, and don't quote me on that, I could be wrong. I believe Cement Quebec is still producing ordinary Portland cement, but all other cement producers across the country has transitioned to Portland limestone cement. And essentially, you're decreasing the clinker content by approximately 10%, and you're increasing the limestone content. So we have up to 5% limestone here. This 5% limestone was adopted in 1983, and then in 2008, I believe 2008 or 2009, it was approved within CSA 3000, which is the cement specification here in Canada, permitted up to 15% limestone. So essentially, you're increasing your limestone replacement level by 10%. And even though you're increasing your limestone content, limestone is more or less traditionally considered an inert material. You achieve equivalent performance since Portland limestone is ground slightly finer than ordinary Portland cement, and also sort of produces things like particle packing, nucleation sites. Calcium carbonate also reacts with aluminate phases to essentially produce an equivalent performance as ordinary Portland cement. Now, in addition to Portland limestone cement, we have supplementary cementing materials, which I mentioned. Obviously, all of them have various different chemical compositions. The most widely used SCM here in Atlantic Canada is fly ash, a byproduct of coal combustion. Approximately 35% of fly ash is sold off for various industries, sort of one of them being concrete construction. The other approximately 65% is landfilled. So up in Belledune, adjacent to sort of, we'll call it the plant, there's sort of acres and acres of landfills where fly ash is landfilled. And the push lately, or sort of the questions is what's going to happen in 2030 or 2040 or 2050. I don't know what the new target is when perhaps coal combustion shuts down, or if it ever does. And the push lately has been on using the fly ash that is landfilled. So in 2019, and then recently, sort of within CSA, there are specifications now on using harvested or reclaimed fly ash, and certainly significant research has been done on using reclaimed fly ash. The top left picture, for those of you from UMB, the late Mike Thomas, who was a professor at the Department of Civil Engineering at UMB. This is sort of a lot of work, or sort of some of the many research he did over the years was looking at the effectiveness of reclaimed harvested fly ash in mitigating things like alkali silk reaction. So fly ash, pozzolanic material, it's very effective in achieving later age strength, low permeability, good durability, but also combating ASR. So ASR is essentially, this presentation is about durability, but ASR essentially, simply speaking, if you have reactive aggregate, your concrete swells and expands. And unfortunately, this is what's happening at the Mactuac Dam, upriver from Fredericton, in Mactuac, New Brunswick. This is sort of work sort of over in sort of this area just to right. These very large blocks were cast. Sort of Mike Thomas is standing there. Approximately sort of 10, 15 years ago when this research was initiated, the New Brunswick Power was questioning perhaps should we remove and replace the dam. So in this case, they looked at what effect sort of using the same reactive aggregate that was used to construct the dam would have in the event 30, 40, 50% processed ash, but also the sort of this block that's off in the distance, 50% reclaimed ash. So in this case, this would have been ash that Mike is seen sort of scooping here into this bucket. So it would have been used. And these blocks are some of the biggest research blocks in the world. I believe they're 10 by 10 by 10 feet. So very large blocks, and essentially ASR expansion measurements essentially look like this. You have expansion on the y-axis, time in years on the x. This is slightly outdated. But essentially, over the years, essentially, you measure expansion, and the goal being reclaimed ash here has been very effective in mitigating ASR compared to a control that doesn't have fly ash that obviously expands. Now, in addition to sort of fly ash, slag, silica fume, which we'll call traditional SEMs, ground glass pozzolan was recently adopted within CSAA 3000 and A23.1 as a supplementary cementing material. So per CSA, you can technically use ground glass pozzolan in a mix, sort of assuming it's specified and permitted on a specification. But ground glass pozzolan, there's essentially three types of glass. There's container glass, which is essentially beer bottle glass, plate glass, which is sort of automobiles or building glass, and e-glass, which is fiberglass. And perhaps one of the push for adopting ground glass pozzolan is certainly it behaves very similar to fly ash, but there's millions of tons of glass that's landfilled on an annual basis, and perhaps unknowns regarding sort of the availability of fly ash amongst other SEMs in the future. So within CSA 3000 and the 2008 edition, they introduced two types of glass, essentially a high and a low alkali glass. And perhaps one of the most sort of famous uses of ground glass pozzolan in Canada to date is the Darwin Bridge in Montreal. I believe service life of 100 years. I mean, if you're familiar with sort of mix design parameters, sort of water cementing ratio, fairly low, sort of typical slump. In this case, they used a blended silica fume and slag cement and replaced 10% of that with glass. So that's just an introduction of common materials that are typically used in mixes. Let me see my time. All right, so moving on to how do I know if a given mix is low carbon? And we're going to pretend in this case that, let's see, my name's Ted. We're going to pretend that I own and operate a ready mix plant in Fredericton, New Brunswick, and I have this theoretical mix. This is a lot of the work I do is developing theoretical mix and working with suppliers across the country and develop mixes sort of on a daily basis for various people. In this case, this is, we'll call it a theoretical mix that achieves an exposure class of C1, compressor strength of 35 MPa at 56 days. This mix contains GUL, so Portland limestone cement. It contains fly ash. We'll call it locally sourced coarse aggregate, fine aggregate, water cementing ratio less than 0.4, and typical admixture dosages for air because this concrete's exposed to freeze thaw and water reducing admixture. So the famous question that people have is, okay, I have this mix. How do I know it's low carbon? What do I need to tell me this is low carbon? Or what modifications do I need to make to this mix to be considered low carbon? And if a concrete specification calls for, let's say, a 10% reduction in global warming potential, can I use this mix? So these are sort of types of questions I get sort of on a weekly basis from suppliers, just because when it comes to low carbon and using low carbon concrete on specification, there really sort of is a knowledge gap. So this example here, these are my proportions, and we're going to assume that my plant is in Fredericton, and each of the stars represent where I currently source materials from. So this star here is fly ash from Belledune, 2 sources locally of coarse and fine aggregate. We're going to assume that I purchased UL from Brookfield, and my admixtures, I'm going to assume, are coming out of Sydney. So with that mix, how do I know that mix is low carbon? So concrete supplied to a job is considered low carbon when its global warming potential. So if we go back to one of the very first slides where we had the 2 cubes of concrete, the mix on the right had a global warming potential, GWP, less than 15% of a baseline. So simply speaking, a mix needs to have a global warming potential less than a baseline. So we'll learn how to develop a global warming potential value for this mix and how to compare it against a baseline. So in the next few slides, we'll learn about what a GWP is, how it's developed, what a baseline is, and sort of how to optimize a mix if needed. So in addition to that, so a global warming potential of a mix is essentially, or simply speaking, a measure of greenhouse gas emissions associated with producing 1 cubic meter of concrete during the production stage. We'll learn here shortly what the production stage is. And a GWP is determined by developing what's known as Environmental Product Declaration, or many people say EPD. So if we look at this schematically over what the process looks like, essentially we have a given mix. We're going to develop an EPD for that mix. Within that EPD, it's essentially like a food label for a mix. It will have a value known as the GWP. So GWPs are essentially kilograms of CO2 equivalent per cubic meter over the production stage, which we'll talk about. We then have this value of 300 for this given mix. We'll then compare it to a regional baseline. We'll be talking about what a regional baseline is and where to find that value. And then we'll compare it to a specification. So in this example here, the requirement is that concrete supplied to a job must have a GWP 20% less than a baseline. This 20% number is sort of at the discretion of the usually structural engineer who's specifying it on a job. Let's say we go through the process and this GWP value is not less than 20%, or as we'll be looking at, all the concrete supplied to a job isn't less than 20%, then we need to go back and we need to optimize this mix. So we might need to sort of play around with sort of the powder contents or whatever it may be to drop that GWP number. So what are EPDs? So I mentioned EPDs are kind of like food labels. So if you look at a chocolate bar or box of cookies or box of cereal or anything with a food label, obviously it'll say how much sugar and calories, etc., are in that per 100 grams or one cookie or whatever it may be. An EPD is very similar to that. It's essentially a food label for a given mix. And this is just an example of an EPD here, declared unit 1 cubic meter. So you can think of that instead as sort of one cookie. And certainly there's a number of metrics here. Many agree that the most important value is this global warming potential. So this value of 306 for this mix here, this is a 35 MPa mix at 56 days. So this is developed using a number of ISO specified rules, and it's developed using life cycle assessment tools. And many suppliers essentially reach out to companies like Athena, who I believe now is Climate Earth, or there's a number of companies on the market that essentially develop EPDs for either ready mix, precast suppliers, and certainly other building materials as well. Now, I mentioned that EPDs sort of within the ready mix and precast world are within the product stage. So if we look at the entire building life cycle for an entire job, obviously there's a production stage, construction stage, use stage, and end of life stage. EPDs for the ready mix and precast are essentially cradle to gate. So they only take into account the emissions associated with manufacturing the raw ingredients. So manufacturing cement or processing aggregate or developing admixtures, transporting all of those materials to the ready mix plant. So if Ted's Ready Mix is buying cement from Brookfield and fly ash from Beldoon and aggregate from Actiquac or Mukto and admixtures from Sydney, sort of obviously all of those materials need to be transported to Fredericton, whether it be by rail or large diesel vehicles. And then the manufacturing. So manufacturing is a little more simpler in the ready mix industry. Essentially, cements are stored in silos, aggregates are usually out in the yard. Essentially, they're proportioned, they're weighed, they're placed in the back of a ready mix truck, and it ends when the ready mix truck gets to the gate. In the precast world, obviously, precast is manufactured under a controlled environment and essentially ends when the element essentially leaves the yard. So to give you sort of an idea, I won't go through all of these, but perhaps things that are taken into account from these various stages. So A1 is the raw material supply. So extraction, manufacturing of all constituent materials, whether it be cement or aggregate. Sorry, A2 is transportation. And A3 is manufacturing. So certainly a lot of data goes into developing the values within this EPD. So if I look at Ted's Ready Mix, who's located in Fredericton, certainly we would sort of take into account all the emissions associated with manufacturing fly ash, my aggregate sources. Obviously, my water is typically just sort of well water or plant water. My cement manufacturing and admixture, and obviously the transportation associated with bringing all of those to Fredericton. Once that's done, we essentially develop what's known as an EPD, which is usually a document that looks like this. Here I have my mixture proportions presented here. And essentially, this is sort of a document that would typically be submitted on a job site. Usually, project specifications require sort of type 1, 2, or 3 EPDs. There's sort of various levels of details of EPDs that are required to be submitted on a job. And from sort of a performance view, once these are developed, you can essentially look at the breakdown of how this EPD or how this value. So for this mix, so Ted's Ready Mix, the mixture proportions that you would have seen, a GWP of 296. We'll talk about whether this 296 number is good or bad here in a second. But essentially, this mix produces a GWP of 296. And the breakdown is essentially material production, A1. And if you look at sort of all of these numbers, regardless if you know what they mean or not, you can see that the production of GUL is essentially the largest number, the largest number here. So if we can find ways to decrease the amount of GUL, perhaps increase the level of fly ash, for example, which has 0 because it's a byproduct of coal combustion, then certainly we will decrease this GWP number. So, so here we have, so I apologize, these numbers are backwards, but this is my plant in Fredericton. Many wonder what happens if you produce concrete at a different location. I mean, certainly there's a number of suppliers that have plants sort of dotted all over Atlantic Canada, or if you're Ontario, Ted's Ready Mix isn't Ontario yet, but let's say I had plants all over Ontario. Certainly, even though my mix proportions are the same, my GWP value could be significantly different depending on where sources of materials are coming from. So this number, I apologize, should be 296, but let's say Ted's Ready Mix in a couple of years decided to move to Halifax, and I decided to sort of maintain all of my same materials. Certainly travel distances may be different, and it could very well be that this number is supposed to be 312. The number increases to 312. Now, certainly, let's say this number didn't meet my specification, which we'll talk about here in a second. we can then look into optimizing mix design. So this is done by a lot of suppliers, depending on the project specification, depending on the reduction limits that are needed. But here we have sort of my typical C1 mix. Total powder content is 410. So GUL is 308, fly ash is 102. If I maintain my fly ash replacement level, which is 25% in this case, I maintain my coarse aggregate content, maintain water just for simplicity in this example, but I increase my powder content, essentially you'll see that your GWP values are increasing. And this is often done by suppliers depending on the specification. And then certainly often sort of cylinders are cast and pre-trials are done just to ensure that sort of these powder contents do in fact achieve a compressive strength of 35 MPa and satisfy your permeability requirement for your C1 concrete. So now that we've essentially developed an EPD for a given mix, how do we essentially know this value of 296 is less than a given baseline? So there's sort of various baseline documents available across the country, really depending what industry you're working in, or perhaps where Ted's Ready Mix is supplying concrete to, or I mean, if you're precast suppliers, what type of element you're producing. The top band essentially presents the 7 regional EPD documents that are available across the country. So in 2002, the CRMCA, so the Canadian Ready Mix Concrete Association, published 7 regional EPD documents for 7 regions across the country. So the first being Atlantic Canada, which is obviously New Brunswick, PEI, Nova Scotia, Newfoundland, Ontario, British Columbia, Saskatchewan, Alberta, Manitoba, and Quebec. And we'll talk here in a second on what these documents, they essentially sort of produce baseline EPD values for a range of concrete mixes, sort of the most widely used concrete mixes within that region. So obviously here in Atlantic Canada, majority of ready mix suppliers use GUL and fly ash. So obviously these baselines are going to be different than Ontario, for example, where majority of suppliers use GUL and slag or different types of Portland cement. So there used to be one national document, and then obviously that didn't make sense just because we're using various SCMs across the country. So in 2002, they published seven regional documents. Now, the documents are slightly different in the precast space, and I'm not an expert in the precast space, but within the precast space, essentially there's 4 documents based on precast elements that are manufactured. So this first document, these are all available on the CPCI website. The first one is for precast panels, architectural panels, structural elements like girders, and then below grade precast elements. Now, within each of these documents, there's essentially baseline EPD values for 3 regions across the country. So there's baseline values for structural elements for Western Canada, Central Canada, and then Eastern Canada. So unlike the ready mix industry that has regional EPDs for 7 regions, here they have 4 distinct documents for various elements and then the regions within each of those documents. So if we look at the ready mix space as an example, this is the document for Atlantic Canada. This document is set to expire in 2027. So I know CRMCA is sort of working to provide a new document that will essentially be valid from 2027 to, I believe, 2032. Essentially, the document presents baseline EPDs for the most widely used mixes in Atlantic Canada. So essentially, this document would have been developed from suppliers across Atlantic Canada, providing data to CRMCA, sort of on cement contents, typical powder contents, typical mix designs for a number of these categories. And from that, they essentially developed a theoretical plan and developed a baseline value that if you're working on a job, sort of a given mix must be less than that baseline value. So one of the mixes, for example, is 35 MPa with air. It's essentially a C1 mix. So if we look back at sort of Ted's ready mix example, so within this document, there's essentially a table. There's 18 different tables for these 18 different categories. And essentially, this is the table. Again, there's sort of a lot of data and parameters. I rarely use anything except for essentially the top number. And essentially the top number, which is essentially in lime green, is essentially the baseline number required for concrete that achieves an exposure class of 35 MPa with air, maximum water cementing ratio of 0.4, exposure class of C1. Now, these tables also are sort of beneficial for suppliers that perhaps might not have access to a life cycle assessment software to sort of develop an EPD that I previously showed you. They can essentially go into this table to sort of benchmark it, give themselves an idea of, let's say I produce a mix with GUL with 20% fly ash. It sort of will have a GWP around 401.54, and then I can perhaps look at sort of what reduction that is compared to a baseline of 474. So now that we sort of have an idea of where to look for baselines, then it comes to whether or not the mix that we developed is less than the baseline and satisfies our specification. And when it comes to specifications, certainly there's a lot more and more specifications are specifying GWP reductions and requiring the concrete supplier to produce EPDs for all the mixes that they're supplying on job. So this is language from a specification that I pulled or that I read 2 or 3 months ago. So essentially achieve a minimum 15% reduction in project-wide GWP compared to the Atlantic Canada baseline. So it's very important that the project specify the baseline document from where the project is essentially occurring. I mean, there are examples that I've seen of sort of projects in Ontario where they reference the BC baseline, which, you know, obviously doesn't make sense. So it's very important that, you know, if the job's in Toronto, they reference the Ontario baseline document. If it's in Vancouver, the BC one. Here in Atlantic Canada, obviously the Atlantic Canada baseline. Concrete suppliers are often needed to supply what are known as type 1, 2, or 3 EPDs. And then the contractor shall determine the global warming potential reduction using something that's known as the concrete carbon project budget method, which we'll talk about here in a second. Now, if we look at federal jobs effective as of December 31st, 2002 that have a value greater or equal than 5 mil and have and supply a minimum of 100 cubic meters of concrete must achieve global warming potential reduction of 10% compared to the regional industry baseline. So the regional industry baseline obviously being the region in which the project occurs. And if you've worked on a federal job, they essentially provide you a table or an Excel file that essentially allows you to calculate total emissions to ensure that you achieve this 10% reduction. So to finish off, I'm just going to briefly go through a little case study on how carbon emissions are calculated. I mentioned this concrete carbon project budget. This is available, or sort of the instructions on how this is done is available in the CRMCA's concrete carbon document. It was recently updated in November of last year. It's available for free online by Googling CRMCA or concrete carbon, or I can share this presentation and provide a link, but it's pretty easy to find. Essentially, the way in which you calculate total emissions on a job is essentially you list all of the elements on the job. So let's say this is some type of building. We have interior footings, slabs, and columns, exposure class N. You specify the strength and the exposure class. Then the maximum GWP is essentially the values from your regional document. So let's say this job here is in Fredericton. We're going to list the baseline EPD values for each of these strength classes. So if we look at this C2, 438.78, we reference the table 12, which is 32 MPa C2 concrete. It has a regional baseline value of 438.78, which is essentially here. Once we do that, we multiply these values by the estimated volume of concrete that will be supplied for each of these elements. And certainly this can be updated later, but before the project starts or when you're about to start the project, you essentially estimate the volumes, you calculate the volume. And this value here, approximately 899,000 kilograms of CO2 equivalent, is essentially the value that you want to enforce on the job. Ideally, you want to enforce this value. You don't want to enforce each of these mix specific values because in many cases, we have specialty mixes that are used on a job. And by specialty mixes, I mean mixes that perhaps require high early strength, or let's say the job spans over 2 or 3 years over winter months. We tend to have cold weather concrete. Cold weather concrete typically sort of requires maybe a higher powder content, a reduced level of SEMs to achieve that higher early strength. That one given mix might have a GWP higher than the baseline. However, if we look over the entire project, we're still hopefully able to achieve that total GWP goal. And then specialty mixes as well. And architectural mixes in some cases have lower aggregate, higher paste to sort of have that nice cream finish on the surface. Low shrinkage, some mixes that require special admixtures. If any of these occur on the job, it's practice under this procedure to multiply the baseline EPDs by 130%. So let's say slabs are being placed over winter. We'll essentially take this baseline value, multiply by 1.3, and that'll essentially change our total GWP for the entire project. That as time progresses, once we develop EPDs for each of these mixes over the job, that at the end of the project, hopefully we're less than 1 million kilograms of CO2. So to quickly look at a case study, I know I'm running out of time. Within this document, there's a number of case studies across the country. In the November edition, so the most recent edition, they included a case study from a job in Atlantic Canada. So this job I was a part of, I was consulted to develop the mixes for this job. This is a Nova Scotia housing project. In this case, Bridgewater Ready Mix in Bridgewater, Nova Scotia. So they retained me to develop the mixes. The goal in this case was to achieve a GWP reduction over the entire project of at least 30%. In this case, they didn't have any special materials or technologies. Essentially, all they had was GUL, fly ash, local coarse and fine aggregate, and typical admixtures. So in this case, this example is within this document. But essentially, we followed the exact same process. In this case, they developed type 3 EPDs for each of the mixes. Anything less than 20 MPa, there's no baseline for. And essentially, in this case, we achieved mixes that over the entire job had a 31.1% reduction in global warming potential, which achieved our 30% target. So my final slide, what are barriers to adopting low carbon concrete? I mean, certainly one of them being education, perhaps an education gap on misunderstanding what low carbon concrete is. Many think we sort of need special technologies or special mixtures. Believe it or not, there's many suppliers that are producing low carbon concrete right now. Unfortunately, they just don't have a way of measuring it. They don't have access to, or they don't want to pay to have type 3 EPDs produced. Number 4 here is cost. I don't know what the accurate number is now, but it used to be that an EPD was sort of in the range of $5,000. That's likely not true now. I'd imagine there's some sort of subscription basis for a lot of these companies to produce type 3 EPDs for you. But I mean, there's many suppliers that, I mean, they're often competing against other suppliers and obviously don't want to have that added cost. Number 2 is limited availability of materials. In some cases, low carbon concrete can be achieved by maybe bringing in a third aggregate source to optimize your gradation. I mean, if you have a downtown ready mix plant, limited silo space, you're likely only going to bring in 2 types of powders. You have limited space for aggregate. You might not have that availability. Specifications is one major barrier. Unfortunately, we still see a lot of prescriptive-based specs, costs I mentioned, and then industry resistant to change. I mean, certainly we are a fairly conservative industry by nature. Perhaps what has worked before should continue to work. So why change anything? So that might be sort of a fifth reason why we're perhaps not seeing more low carbon concrete. So with that, I'd like to thank you all very much. Went a few minutes over, but yeah, thank you.
No, that was great. I do have a bunch of questions listed here, but what I might do, just in the interest of time, I noticed quite a few had to drop off as when round 2 hit. If you're okay with us emailing a few questions, and we can include that maybe in the blog that we write after, and
Sure.
And send out your slides as well, if that works for you.
Yep.
I guess just since I have you right now, I'm going to ask one question. The big, and I noticed you, like, your barrier was around cost, and that's where I was going to go. Like, obviously there's a lot of discussion, especially since 2020, about the cost of construction. A lot of what the OCRC does has been in vertical infrastructure, different forms of buildings, and lately a lot of housing. But I mean, that's really, the cost of construction has gone up substantially over the last 6 years, and with everything happening in the world, is likely to go up even more with oil prices and so on. So is there currently a premium for low carbon concrete? And I'm mindful that there's like short-term versus long-term thinking, but just curious if there is a premium there, or is it project specific?
Yeah, I'd say it's project specific. I mean, the premium, you could argue there. I mean, there's really, I mean, sort of, if we look at the definition of what low carbon concrete is, there's no compromise to performance or durability. So, I mean, many think perhaps, I mean, there are many myths about low carbon concrete, which I didn't touch upon, but yeah, I think it's probably project specific.
Yeah, no, that makes sense. Yeah, no, it's good to know. And I was going to get into like what the different plants and if there's anything required from their side. And you talked about kind of the education gap. I mean, whether it's prefab construction or any kind of new innovative technology or material, there's always like a cultural and education gap associated with it. So I'll forward you some questions that I had about that, and maybe we can include it when we send out the link to the attendees and stuff.
Yep, sounds good.
That's great. All right. Well, thank you, Ted. And for folks on the line, we're having our next webinar. I believe it's April 16th. It's with Dr. Andrew Fisher, who is a new professor in AI with computer science at UNB. All of his research to date has been focused on the use of AI in construction. So it should be a pretty interesting conversation. So with that, I'll let everyone go. Have a good rest of your week, and we'll talk soon.